All right, good afternoon, class. Can you hear me okay? Can I get your attention? Welcome to the class. Unfortunately, I don't have my regular laptop today because I forgot to get my laptop. I did have my iPad, and I got a loaner laptop from CSEF, which is Computer Science for IT, except I have only support for HDMI, which is actually better and newer than VGA. Except I've never been able to get HDMI to work on this, so I just called a tech support person who was like over here in a few minutes. In the meantime, I'm going to try to do a lecture without you guys having access to the slides that I had planned for. So bear with me, it's likely to be slower than usual because I won't have the pictures to show you for that. Hopefully, we'll figure out what's wrong with this. Yeah.
Should we pull up the slides on our computer?
Oh, by all means, yes. The slides are up to date. So if you can follow the slides. In fact, if you don't have a computer, if you can sit with somebody who can just show you the slides, that's perfect. I'll read out like what slide number or the picture I'm expecting you to see. All right. Sorry about this. Hopefully this just gets figured out in a few minutes. All right, so I'm looking at slide 42, chapter 4, right? We're on chapter 4. Today's agenda is, guys, look at your slides, but don't talk. give me your attention, please. Today's agenda is, having looked at schedulers and what's inside or outer, and a very high-level overview of control plane and data plane separation in the network layer. We're going to dive a little deeper and look into what the IPv4 specifically, the IP protocol itself is, right? IP stands for Internet Protocol, so presumably it's the most important protocol on the internet. It indeed is, but it's actually the simplest, most mundane protocol. In fact, calling it a protocol is a little bit of a misnomer. It's more of a header format than anything else. It is its simplicity that is its strength. Okay? I'm going to assign DHCP as just homework reading for yourself. Read it by yourself. It's a fairly simple protocol, but I will cover in class network address translation, and then look at what V6, the newer version of IP that most of us actually don't use, how it differs from V4. Then conclude with the SDN way of doing forwarding today. I said SDN is a powerful paradigm. It allows for great ease of management, greater programmability in the network. So we'll look briefly at what this means. Hopefully, by the end of it. Well, see, that's what happens. Hopefully somebody's coming. Okay, so if you walk through the animation in slide 42, it shows you a few things at the network layer, right? So we've seen a little bit of the control plane and data plane, how the control plane computes shortest paths and feeds into the data plane's forwarding table. There are a few other protocols at the network layer, one of them being ICMP. This is the ping. This is the protocol that ping uses by default. You can also write ping on top using UDP or TCP, but ICMP is primarily what it is a protocol that exists for debugging purposes. And then there is the IP protocol itself at that layer, right? So there's a fair amount of complex functionality going on in the network layer. The network layer, I'd say, is the single most architecturally important layer in the network stack. It is what holds together everything above it and everything below it. So the internet is often referred to as an hourglass design, where the thin waist, the narrow waist of the hourglass is IP. Okay. Why do we refer to it this way? Because there's a staggering diversity. We've only seen TCP and UDP, but there's many transport protocols beyond those. There's a staggering diversity of applications on top of, so it sometimes winks and comes on, but for the most part it just is blank. And this happens on this, and the previous laptop as well. So we're looking at this out. Why do we call this an hourglass? There is a staggering diversity of protocols above and below, specifically application level protocols, right? It's immense. Like you can write whatever program you want. You now know how to do it using sockets. Below also we have a lot of diversity. We haven't quite seen the link layer, but you have a wide variety of link layer protocols as well as the PHY layer or physical layer. The physical media, we've seen a bunch of physical media in chapter 1 at a very high level, right? Wired and wireless, and even among wired cable and optical. Wireless can be satellite, Wi-Fi, LTE, and so on, right? All of this is held together by this glue, this IP. It's a very narrow protocol. If you want to be on the internet, you want to be able to speak this IP protocol, but above and below you can do a lot of things as per your application or your stack needs. How did you, well, see. I'll use my iPad one time for keeping track of my own train of thought. Okay, so if you look at slide 43, that shows you the IP header, okay? Just like we saw the UDP and TCP headers before, another DNS, HTTP, SMTP, and so on, this is the entire IP header, okay? Every single packet on the internet carries this header. If you look at the header, this is the usual convention for displaying headers. It's 4 bytes in each row, 32 bits of 4 bytes in each row, and there's 5 rows that are a necessity in an IP header, okay? But don't look at what the projector is saying, because that's not in the right slide. So there's 5 times 4 bytes, 40 bytes of IP header, or IPv4 header. That's the IPv4 protocol. It is what carries, to this day, the overwhelming majority of packets on the internet, okay? I'll say a little bit about what V6 is, how it's been around for 3 decades, but it's not what's kind of dominant on the internet. So if you look at the headers, you see a few fields, a version number to distinguish between V4 and V6, header length, type of service. Type of service can tell you things like whether differentiated services is being used. Oh, so is there something I need to be careful about so that I don't go into the problem?
Give you an adapter for the.
Oh, okay.
I might come in and try and change some settings. Classes, now if you leave this in the drawer here.
Please do. Yeah, thank you. Thank you. Okay, so that's the complete IP header. You see a header length. This is the header length. Okay, this is saying how long. Oh, I still have my this thing. So it's harder than it looks. Okay, hopefully you're set. Alright, so that header length field is giving you the length of the IP header. And notice that the first 5 rows, these 40 bytes, 5 times 4 bytes, right? That's there, that's always there. But IP also has support for some options, which may or may not exist in the header, right? And so that's why a header length needs to tell you like when the header ends and when the packet starts. The payload after that will typically be a transport segment, so TCP or UDP if one of those protocols is being used. How would we know if it's TCP, what the length of the payload is? We also need to know the length of the payload. How would we know that? So this header length is telling you the length of the header. Here there's a total length already of the datagram. If you go back to the TCP header, can one of you go back to the TCP header and tell me if there is a TCP, in TCP, the length field, is that the payload length or the header length? Go back to one of the TCP chapter 3 slides and tell me that. If we have the header length and we have the total length, we don't know the number of options. There's still one variable missing. And so the length field in the transport layer header, which is slightly different in UDP and TCP, is going to be important to be able to determine what the exact lengths of different portions are. Okay, so that's something to keep in mind. What other fields are there? Oh, sorry, I keep clicking. Type of service, we've seen one of these differentiated services we saw at a high level. It's just called prioritization of traffic. We saw what ECN bits are for, explicit congestion notification. We saw those 2 bits, right? So the 6th and 7th bits are being used for ECN. That's part of the IP header. So when there is congestion, there's no room in the congestion control is TCP's job, but in the TCP header there's no space. There's no room for marking congestion. So we do that in the IP header. It's all going to be encapsulated by IP when the ACK comes back, so it carries that information. The second row is about fragmentation. We'll look at it in a second, but it's about chopping an IP, too big IP packet. An IP packet that's bigger than a router can handle will be fragmented into smaller IP packets and then reassembled before being delivered to the end. So that's what the second row is for. Let's jump over for now to the third row. We'll look at how fragmentation works exactly. So we see a time to live field here, right? This time to this TTL is what's used in what tool that we have seen before. Where did we see the use of a TTL? We saw this in chapter 1. Yeah, right? Yeah, trace stuff. So if you're able to get hop-wise latencies by limiting the time to live, or really it says time, but it's number of hops, it's decrement per hop. So that's in the IP header. Then you see this thing called an upper layer. What do people think this upper layer is for? Yeah? What protocol? The payload, right? Whether it's TCP or UDP or DCCP or RTP or whatever transport protocols they use. I'm going to close the door. So that's the place where the network layer, when it gets an IP datagram, how does it know whether to process what starts from this place, the payload, whether to expect a TCP header there, whether to expect a UDP or what transport header. So the 4 byte number there, no, not 4 bytes, but 4-bit number there is what tells you what the upper layer header is. Okay. All right. So checksum. Header checksum. Self-explanatory. This checksum, unlike UDP, is a header checksum. Okay, so the payload checksum will be part of the transport layer header. So you have checksum redundancy at multiple levels, and the checksums are also over slightly different portions of the packet. So IP header is protected by its own header checksum. And of course, the 2 most important fields. Every layer in the stack we've seen has its source and destination identifier. At the transport level, the source and destination identifier is the source port and destination port. At the network layer, this is source IP and destination IP address. At the link layer, the source MAC address, destination MAC address. Right, so source and destination is part of the header at every layer, and then there's a few other things depending on the function. Right? So that's about most of what you need to know about IPv4. The options, examples of options include, say, here an example is a record route option. So trace route does this to some extent, but record route is an option, for example, you can set to explicitly record the route that's being traversed by an IP packet, instead of having to use like TTL limited trace route type tools. Record route will just explicitly record in the packet itself what the route is. So there's a bunch of other options like this, mostly for management, debugging like purposes, overlapping high-level goals, but distinct in specific functionality from ICMP, which is explicitly for management. Okay, so header overhead. TCP also had 20 bytes of header. IPv4, sorry, I've been saying 40. That's 4 bytes times 5 is 20, right? So IP is just 20, not 40. TCP plus IP combined is 40 bytes of total header. And if you go to the MAC header, there's about something on the order of close to 20 bytes, nearly 20 bytes of header there as well. And so a typical packet carries about 60 bytes of header. So if you're doing SSH, for example, typing one character, generally our speed of typing is too slow compared to the network transmission speeds. And so every character is essentially being sent in its own packet. So for sending 1 byte, you're using up 60 bytes of header. So that's the worst case overhead. But if you look at a more common, a more typical packet size or MTU on most networks, 1500 bytes, then 60 bytes of header, it's not negligible, but it's not a big percentage of an overhead. But that's the overhead you're talking about, right? Okay. IP addressing. We are all familiar with this IP address structure. It's, and given how much people rely on the internet, it's most lay people even are familiar with some notion of an IP address, right? To some extent. Why is the IP address structure the way it is? That's the next question we're going to delve into. So this shows you a network of 3 subnets, those blue things. The word subnet has a formal meaning that I'll introduce in just a little bit. And a bunch of hosts, each of which has an interface that has an IP address and a router that also has a few interfaces. Each of those interfaces also has an IP address. So an IP address is a 32-bit identifier associated with a host or router interface. The way you need to read this, as I also told you back in chapter 1, it's a host or router parentheses interface. So it's a host interface or a router interface. An IP address doesn't identify a host. In general, it identifies an interface. There's only one interface in a host, then it's synonymous with the host. But in general, devices have more than one interface. Okay. So what is an interface? This is where the physical connection, the link, this is the line termination point. We are going to look at IPv4 first. So 4 byte addresses. Each of those is 1 byte long. So here's an example of 2. So the address 223.1.1.1, that's the dotted notation to which we separated. That's how the IP address is characterized, right? Okay. So this says this is a textbook that says host is 1 or 2 interfaces. This is true. Most laptops, desktop computers will have typically a wired Ethernet interface, a wireless Wi-Fi interface, a virtual local host interface, possibly others depending on the nature of the machine, right? Enterprise class servers can have more, but hosts generally have a small number of interfaces. Routers, it's common to have many interfaces, tens of interfaces on routers. Those inputs and outputs stuff. It's fairly common. Okay. So let's pause for a second and ask, how are those physical links actually connected to those interfaces, those wires, right? What does it mean for the router there, this interface, to be connected to all of these 3 hosts? Well, for now, you can mentally abstract it as just a cable with T connectors. So it's just one long cable that can be split along the way to connect more than one host. Okay, like a T-junction. Use multiple T-junctions. In practice, you have link layer devices that we haven't yet seen. So in practice, when we're going to see in the either an Ethernet switch or a Wi-Fi base station, depending on whether it's wired or wireless. For now, we're going to abstract out these link layer devices and essentially think of them as equivalent to just, there being nothing, just a wire connecting them, right? And that's actually a fairly reasonable way to think about it too, but because these islands are all broadcasting to anything anyone says, as you know, through Wireshark, everyone can hear, right? Because these are all like local area networks here. Okay, so I told you subnets have a formal meaning, okay? Those blue thingies that you see on this slide, those are called subnets. So what does a subnet mean exactly? In this picture, you have these three areas, contiguous regions that are contiguous without ever hitting a router. So in order to go from any machine here to any machine here, or anywhere in this blue island, you don't have to go through an intervening router. And so that is the fundamental defining property of a subnet, which is interfaces, this is the contiguous portion of the network, to reach every bit of which you do not have to pass through an intervening router. Okay, so if it helps, one way to think about this is, I mean, think of these are waters, this is like a frozen ice island, if you will. If you have to go from here to here, or any portion of the network to another portion of the network, you can't just swim through it, you have to jump onto ice and go over it, then you're moving out of your subnet to a different subnet, right? The analogy doesn't stretch very well, so like, what are these white portions? They're nothing, they're only this. So it's a contiguous portion of the network, to traverse which you don't need to go through an intervening router. That defines the subnet, okay? An IP address, the reason the structure has this dotted notation 4-byte structure is because it's a little bit like postal addresses. Okay, in a postal address you have well, if you were doing international mail, you would first start with the country, and then there's an area code, and after that there is a street name, then there is a building number, possibly an apartment number. So it's zooming in, right? It's naming the location of something. IP addresses are doing exactly that. An IP address is identifies or names a location in the network. This address may change over time depending on where this interface is connecting. So it's not a fixed property of an interface. It's not a hardware level burned into wrong kind of property. That's a MAC address as we've seen. Okay, so the structure has a subnet portion of the address that identifies which local end network it belongs to, and then a host portion that identifies specifically which exactly is the interface. It's essentially an interface. Okay. So in this example, we have 3 subnets. What is the recipe in general? It's a little bit non-trivial. You may look at this picture and think, okay, now I understand what subnets are, but let's make sure that we truly understand what subnets are. What's the recipe for determining how many subnets are there in the network? Well, detach every link from the interface to which it's connected, and then count the number of disconnected portions of the network that you have left, right? That's the recipe for doing this. So in this case, if you detach every host and every router at its connection point, then you're left with 3 islands. That's 3 subnets, 3 contiguous portions of the network. Okay? The reason I said it's non-trivial is, well, so let's make sure that we understand what the naming convention, the addressing convention for the subnets are. We will denote the subnet portion of the address using this notation, the slashed notation, which is a.b.c.e /x. Okay. So in this example subnet, this is 223.1.3.0/24. A /24 subnet has how many addresses in it? Yeah?
256.
Yeah. So So a.b.c.d/x, when we write it like this portion refers to the subnet mask. How many addresses does this subnet have? a.b.c.d/x. Well, Jason.
2 to the 32 minus x.
Correct. 2 to the 32 minus x. What is this notation saying? It is saying that the first x bits in these 32 bits are fixed. That's the subnet. And the rest are floating. They're wildcards. Okay? X bits are fixed. 32 minus x bits are floating. So that's the number of host addresses that fit into that subnet block. Okay, so we need to keep this in mind. And so the other subnets, these are all, in this example, they nicely fit in the boundaries of bytes, right? So it's a /24, which means the first 3 bytes are fixed, first 24 bits or 3 bytes are fixed, the last 8 bits or the last byte is floating. In general, this boundary doesn't have to be at an exact byte. We'll see that shortly, right? So these are all /24s with those respective subnet addresses. Okay, so now to make sure that we understand this recipe for determining subnets, the question is, how many subnets are there in this picture? Let's see. I think there are chances somebody else might want to answer. If there's no one, okay, Tom. Okay. How did we get there? Do people see there are 6 subnets here? It's not 3 subnets anymore. Well, you can see 6 blue regions in the slide, right? So that's, maybe that gives you a hint already. But we need to be careful. We go about by doing the same recipe. We detach hosts and routers from the interfaces they're connected to, and then look at the connected or contiguous portions of the network that we are left with. There's 6 contiguous regions in this network. So the catch here is that each one of these is also a subnet. To go from here to here, we need to go through an intervening router, which here is not available. So it makes it really clear by detaching hosts and routers, whatever contiguous portions you're left with, that makes it really clear what the subnets are, right? And so in this example, those subnets have those respective addresses. In this example also, they happen to be /24, which means x is 24. But in general, it doesn't have to be an exact number. Okay? /24 subnets are very common, but it doesn't have to be /24. What all could it be? Well, that's the question that's answered by the notion of CIDR prefixes. So this notation, a.b.c.d/x, is known as a CIDR prefix. A prefix, a CIDR prefix, same thing. CIDR stands for classless interdomain routing. Before CIDR prefixes existed, we had a different way of allocating IP addresses. We had 3 classes of addresses called Class A addresses, Class B addresses, and Class C addresses. Okay. So we said Class A addresses are /8, /B addresses are /16, /C addresses are /24. So really small organizations that had just the order of 100 machines or so could make do with a /C prefix, okay? Because /C, but /24 has 256 addresses. How many does the /8 have? How many addresses does the /A8 prefix have? 2 to the 32 minus 8, that's 2 to the 24. That's a fairly big number, okay? That's 16 million. 2 to the 20 is million. 2 to the 10 is 1,000, approximately 1,024 is approximately 1,000, right? So it's about 16 million addresses. That's a really huge organization. So this is what we did. We doled out IP address blocks in these sizes. So we said, if you became an organization that was too big for 256 addresses, then you get 65,000 addresses. Okay, this is 256, that's 16 million. If you become too big, if you outgrow 65,000 addresses, then you go to 16 million. This is obviously a waste of IP address blocks. You're not using them very efficiently. So instead, we went to these cigar blocks around early 90s when it became apparent with the growth of the internet, even back then, that we're going to run out of IP addresses very soon, IPv4 addresses very soon. That's also when in the 90s IPv6 came out. So now we have this A.B.C.D notation where X doesn't have to be at byte boundaries, it could be anything. So it's much more understandable to say, okay, if you outgrow your /24, which has only 256, well, we'll give you 512 addresses. 512 addresses is /what? This is 256. If you want 512, that would be a /23. Okay, so you get upgraded. You can acquire a /23 prefix to have double the number of addresses. This is much more reasonable, right? If you outgrow this, you go to the double level, and then from 512 you go to 1024 and so on, than jumping across class C, class B, class A. So we no longer use this terminology of class A, B, C addresses. Just everything is a civil prefix, okay? Right, so that's the subnet part, that's the host part. So IP addresses, how do you actually get these IP addresses? When I said we were, in quotes, doling out /A's or /B's or /C's back then, and it became very clear we'll run out of IP addresses. Who is we? Who is doling out these addresses? Who gives you these IP addresses? Who gives you the host address? Who gives you the subnet portion of the address? The host address is the easy part. When you go to a coffee shop and connect to the Wi-Fi network there, or an airport, or any public place, or home for that matter, or the department, computer science, right? Your IP address is changing. You can go to your network references, you can look at what your IP address is. Sometimes it's a publicly addressable IP address. In some cases, it will not be. It will be a private IP address, which means outside entities cannot make first contact. But how does this host, when it moves around from home to a coffee shop to a workplace to an airport with changing IP addresses, how does it get this IP address? Who gives it this IP address? Yeah, Omri? Yeah, it comes through the router. It's fair to say it comes from the router. Any guesses on what the protocol might be that gives you this address? There's a very common protocol that gives a host an IP address. It's almost universally used. Okay, it's not the only protocol, but it's the most common protocol for doing so. That protocol is DHCP, okay, Dynamic Host Configuration Protocol. It's dynamic. As you move around, it all automatically connect. It gives you an IP address. I'm going to skip over DHCP, and it's a fairly simple protocol. If you're curious about it, you go to a coffee shop, how do you get an IP address? Read up on DHCP from the textbook, all right? I'm going to address the other side of the question, which is, how does a network get the subnet portion of the address? So now we said your router gives you the address here. Router will generally speak DHCP with your computer and give you that address. But how did that router get that IP address? Well, the answer to that is whoever it gets internet service from, that thing gave it its IP address. So at home, if you have cable modem, you get one IP address. That's internet facing, that's your public IP address. Inside the home, you have many machines, but that's what NATs do for you. Okay? They hide those many internal IP addresses and multiplex all of them into one public facing IP address, which your cable modem service provider can. It's the same way for UMass. UMass owns this prefix, more than this prefix, but it certainly owns this. These 65,000 addresses, 128, 119. So this is why, take any UMass name, like just ns.dig www.cs.umass.edu, which is any ECE or UMass or any department, they'll generally fall in this range. UMass owns more than just this, but this is the biggest block of addresses that it owns. Who gave UMass this group? Inside UMass, DHCP is being used at the department level to give addresses to hosts. But who gave UMass this address? whoever is giving it internet service. Okay, so UMass has at least 3 ISPs that provide it commercial. Well, 2 of them are commercial, one of them is an educational one, is non-profit research network. Those ISPs gave UMass this block of IP addresses. Okay, so, oops. So here's an example where an ISP has a /20. The /20 is truly 12, which is about 4,000 IP addresses. And if it provides internet service to 8 organizations, in this example, it might split its IP address block of 4,000 across these 8 organizations, giving each a /23, which we know is 5 whole addresses each, so 5 programs, 4,000. Okay, so nicely fits 8 organizations here. Okay, so your internet service provider gives you the block of IP addresses. How does it get that block of IP addresses? It just totals all the way down, like it gets it from its higher tier ISP, and what happens when you get to tier 1 ISPs, the largest ISPs? I said there's about like 10 or so of them in the world. For looking at that question, let's look at how hierarchy in this IP address is immensely valuable to making routing scalable through the process of aggregation of addresses into prefixes. So here's in this example, it shows you 2 ISPs. One of them is a shadier ISP called Fly by Night. The other is this, the ISPs are us. There's 8 organizations, there's /23 we saw on the previous slide, right? These ISPs are giving you addresses, these organizations from their block that they own, that they somehow got. We haven't answered how they got it yet. Their job as part of providing you an organization internet service is fundamentally to announce to the rest of the internet, like they're doing here. If anyone wants to reach 200.23.16.0/20, if anyone wants to reach the 4,000 addresses in that block, please send packets this way. That's what they're doing. They're advertising your addresses to the rest of the network, the rest of the internet, so the rest of the internet is able to reach you. So they're making you reachable on the internet by advertising your prefix. ISP-RS is doing that too. It owns a different prefix, and that happens to be /16 or about 65,000 addresses. So look at the amount of compression that's happening here. 32-bit IP addresses mean a total of 4 billion or 2 to the 32 possible IPv4 addresses, right? Sometime back, last week I think, I told you that even core routers, the biggest number of prefixes in core routers is less than 500K. Okay, less than 500,000. Okay. Router memory is expensive, the content is full memory into which you index and you figure out what the output port is. They don't have individual IP addresses. They don't have 4 billion entries. Okay. They have something more like 400,000 entries. So there's 4 billion going down in the worst case, okay? Often they might be far, far lesser, but rarely routers have much more than 500,000. This is a 10,000x compression. Instead of individually keeping each IP address in your forwarding tables, routers are only storing these prefixes that on average is giving you a 10,000x reduction in the amount of memory. This is TCAM memory, needs to be blazing fast, it's expensive, right? So we rely on aggregation, like here, for scale. This is what Silver prefixes enables for us. There is another very handy feature that this style of routing enables, and it goes hand in hand synergistically with another forwarding aspect we've seen called longest prefix matching. So in this example, suppose organization 1 doesn't like its shady ISP and decides, I don't want your service, you're not good enough, the speeds are not good enough, or they're flaky, I'm going to move to ISPs or us, right? Like we change cellular provider. You don't like AT&T, go to Verizon. You don't like Verizon, you go back to AT&T, you only have 2 or 3 choices, unfortunately. So, if that happens, Organization 1 moves from Fly by Night to ISPs R Us, that's the change in network. So, at this point, this router that was announcing this address, this /16 prefix, has a little bit of seemingly a little bit of a problem. It has to announce that prefix, and it also has to announce the prefix here, which this organization can retain, depending on like who owns that address block, whether it actually got it from its ISP or whether it actually owns the block. If it owns the block, it can actually can just keep the block. Okay. It doesn't have to renumber every single host in its network. It can just re-cable, connect to a router in ISPs R Us, keeping its address block. And at this point, ISPs R Us is going to make 2 announcements. This has increased its work a little bit. Earlier, each ISP was announcing to their advertising to the restaurant one block. Now, one of the ISPs is, because some displacement has occurred, one of the ISPs is having to announce 2 blocks. Okay? This might seem like potentially problematic, right? Because you have this being announced here, this is the /23, but this /23 also belongs to this /20. Right? The /20 is a superset of addresses contained in this /20. What happens to a router that receives both this advertisement and this advertisement? Does it send packets to organization 1 this way, which would be incorrect, because there is no organization 1 connected here? Or does it send it this way, which would be correct, but how does the router know if it gets 2 different advertisements from 2 different networks to which it's connected? We know the answer. What's the answer? Longest prefix matching, right? This is the longer match. So the router will pick the longer match. They will pick the /23 match, and therefore correctly route to organization 1. So organizations can keep their address block and switch providers easily without having to renumber IP addresses, which is a convenience. And changing IP addresses, DNS does caching, things can be down for like half a day, possibly even more in some cases. It's a headache, so not having to renumber is a good thing. Okay, and IP addresses, hierarchical aggregatability combined with longest prefix matching all comes into it. Okay. So the last question being, okay, who actually gave the ISP, or in this organization 1 example that owned the block, the /23, how did it get it? Who is the ultimate arbiter of these IP addresses? It's not turtles all the way, it ends, the buck stops at an ultimate authority for the entire internet. We have seen this authority before. Any guesses? It's not FCC. Anyone else? Yeah? ICANN, International Corporation of Assigned Names and Numbers. The numbers part refers to IP addresses. Okay? So we saw ICANN in the context of DNS, right? If you decide you want an address like whitehouse.gov or barackobama.com or org or whatever, who decides whether you can rightfully get that name? What if you swoop on a naming and get it in the hope that it becomes very popular? That's also a business, it's a legitimate business these days, but in some cases it can be illegal to do so. Who decides in the case of disputes who owns what name, what DNS name? Well, it was ICANN. ICANN also controls root DNS. So at the very top level, this international corporation, it is a corporation, and it's an international corporation. For the longest time, even though it's called an international corporation, it was largely controlled by the US, and the US still, for various geopolitical reasons, exerts a lot of control on this, but increasingly so it's become more and more global in nature. right? It's meant to be an international organization. That's the ultimate arbiter of any adjudication involving either names, DNS names, or IP addresses, numbers. Okay, IP addresses, are there enough of them? So as I told you that we already knew back in the 90s that we were running out of IP addresses. We made the transition from class ABC style addresses to serial prefixes. So we were not going to run out of them as soon, as quickly, but still, it was very clear the rate of, in the rate of growth, the exponential growth of the internet, that we'll run out of them very soon, right? And in 2011, the last chunk of IPv4 addresses was officially exhausted. So organizations employ a bunch of techniques to just reuse IP addresses over time, right? When you go to Amazon and get an EC2 container or a virtual machine, you spawn up like hundreds of these machines to have a server farm, a virtual server farm, without having to keep your own infrastructure. Amazon has to play a bunch of tricks to take the limited number of IP addresses it has and rotate them across these images to do some kind of translation, one of which is network address translation. To get around this problem of a finite and rather small, even though 4 billion might seem big, it's small compared to the number of devices we have on the internet, right? By any measure, if you try to count the number of devices, most people, even in developed, sort of, irrespective of the GDP of the country, most people these days, the majority of people in the world these days have a smartphone, an internet-capable smartphone, right? Many of them, that's all they have. But most people in developed countries have a few devices that are internet connected. To be on the internet, you need an IP address, right? The world's population is something close to 8 billion, so you can do the math, and this is not counting data centers, server farms, and all that. 4 billion is nothing, right? And then if you go to like sensors and tiny smart dust and whatnot, then you're looking at an insane number of devices. So 4 billion is nothing. It's a tiny number compared to the total demand we have. IPv6 systematically is the version of IP intended to address that problem. We're not going to run out of IP addresses anytime soon, ever. Tell you why. But in the meantime, as a stopgap measure, we started, since sometime in the 90s, we started relying on network address translators. NATS, or network address translation, came about as a stopgap measure, recognizing that IPv4 address space is going to be exhausted very soon. It's not going to be an easy step to transition from V4 to V6. People recognize that too, right? A lot of things are going to break in transitioning from V4 to V6. Not everybody will have support for V6. It's going to be a gradual process, excuse me. In the meantime, we need something to see us through. And so NAT started out as a stopgap measure for that. IPv6 has plenty of addresses, the address spaces overall, right? In case you're thinking, oh, okay, that's what we said for IPv4, wait till we get to 2050. No, not quite. I mean, this number is greater than the number of atoms in the universe, the known universe. So we're not going to run out of the address space here. However, our problem today is, having started out with the stopgap measure of NAT, intended to tide us over in this transition from V4 to V6, it's been 3 decades now, and we are still largely using V4 and NATs. What came about as really a hack, there's some inelegance about NATs. Some of that has come to be viewed as not a bug, but a feature. Okay? And the rest, well, it is what it is. We stick around with NATs. What are NATs? NAT stands for Network Address Translation. They translate addresses from public-facing, publicly addressable addresses to private addresses. So what we said was, not all of these 4 billion IP addresses are public IP addresses. Some of these addresses, we know one of these addresses, 127.0.0.1, this is localhost or a virtual interfaces IP address, right? It's just a software port, it's not an actual hardware interface. there's quite a few addresses like this, some blocks. So blocks starting with 10.0, for example, blocks starting with 192.168. I forget what the size of that block is. These are all private IP addresses. So if you send a packet to 127.0.0.1, it's not going to go anywhere. It's just going to loop back. It's also called a loop back interface. If you send packets to like one of the 10.0s or one of these private IP address blocks, there's many machines in the world that have that address, and they won't be reachable. So the packets won't go anywhere. So that's what the private addresses mean. And so in this example, say datagrams with the source of destination address in this private block, this 10.0.0/24, they're all part of this NAT group. This could be a home, a residential, or even a small enterprise network. Okay? The internet service provider would have given, so if you have a cable modem network, this could be a household network of a few machines. You got one IP address from your provider, that's the publicly visible IP address. In this example, that's 138.76.29.7. So any datagram that is sent by any host inside the NAT, when it steps out to the internet, it will have the source address of 138, whatever the rest is. Any datagram that is coming from the internet will have a destination IP address of that same 138.76.29.7. When it gets to this NAT router, it is going to magically find its way back to wherever it is destined, wherever it had originated from. This gives you an idea that machines behind NATs can't, to machines behind NATs, you cannot initiate communication. You can only give them responses to the communication they have initiated from inside the NAT. It'll become very clear what I mean by this in a second, right? So all devices in this local network, they have addresses from the private address space. So those are examples of private address spaces. You have some nice advantages. You just need one public IP address, so your internet service provider doesn't have to give you multiple IP addresses, doesn't give you a block. Every household just gets one IP address. You can renumber all those 10.0 addresses inside the house or office or whatever, small business. Nothing will break. Okay, because everything gets translated to this public-facing IP address. And there is a security benefit though. This is what I meant by saying NATs came about as a stopgap measure, but some of its bugs or things that they break actually are also viewed as features in some respect. The one philosophy of the internet is open communication. IP addresses are meant to be addressable globally. Anybody can communicate with anybody else. It has pros and cons. If you can send a packet to anybody, you can do denial of service attacks on that entity, right? But open or free, unrestricted communication has its own pluses and minuses. NATs break this paradigm of unrestricted communication to any IP address. They don't allow an outside entity to initiate communication. NATs work from our homes. We all use NATs. Most home networks use NATs. Right? It's extremely unlikely that you're not using NATs in a residential network. Everything seems to work fine, right? Zoom works fine, internet, web, mail, everything, Skype, whatever works just fine. Every single application you're using from your home initiates communication from inside the home to the internet. It's never the other way around. A server from the internet will never make first contact with any machine in your house. It cannot. Why? Because it'll come. What can it do? It'll come to this place. If somebody tries to initiate communication from outside, it'll come all the way here, and this router will not find a matching entry to know what to do with this outside communication, because it won't match any record it has of communication initiated from inside the network. So it'll simply drop that. So this breaks the any-to-any free communication model, but this is also seen as a plus because this is the easiest way. Most residential internet users, they're not tech savvy. They don't know how to manage their network. They don't necessarily keep up to date with security patches. The fact that outside entities cannot initiate communication with them is a huge security plus. right? Because then you are responsible for whatever website, whatever addresses you're contacting. And that's much easier for most people to handle. There's still all kinds of security break-ins that happen. It's a huge security plus to not be able to initiate communication with the outside. So it's both a bug and a feature, and how you look at it depends on whether you're an architectural purist that thinks there should be free and open communication between any devices on the internet, or whether you're more of a pragmatist. Okay. Anyway, NATs are here to stay. This doesn't look like. I'll skip over this slide because I'm going to show you how it works securely. It's a lot easier to understand that way. So that's your home network. Your router, if you have a buy a Wi-Fi base station, it'll have support for all these NATing capabilities over there, right? I told you everything in networking is done by throwing a cable at it, right? This is to a large extent. So here you have another cable that kind of looks a little bit like a forwarding cable, two columns, with the difference that it's not translating an address to an output port. Instead, it is translating an address to an address. That's why it's called network address translation. Notice that all the addresses inside the network have a 10.0 address. There's only one publicly addressable address. So outside entities can send addresses to 138.76 address. Communication can only be initiated from inside. Okay. So if two of you are doing Zoom calls from home, from your respective homes, how does your Zoom initiation get inside the other person's network? If communication can only be initiated from inside to outside, not the other way around. Well, let's put that question on the stack. Let's look at how these NACs are working, okay? Which will make it clear why communication from outside cannot come in. For any communication initiated from inside, that is how the packet is going to look like. It's going to have a source address of 10.0, a source port, in this example of 3345. How did that source port come about? You know how it came about. It was whatever port was available, the operating system was assigned at that port. It's just the local port of that socket. It's destined to some 128.119, which is the UMass address, of course, to a web server. Some web server at UMass is where it's destined to. When the router gets this packet, it's going to do some address translation. It's going to replace the source address from 10.0 to that public-facing source address. It's not going to change anything to the destination. It has to go to the UMass web service. It's not going to change anything to the source, to the destination IP address, destination port number. But what it has done is change the source, both IP and port. It's changed the source IP to the public-facing IP. It's changed the source port also from 3345 in this example to 5001, and it's kept a mapping between the two to remember that it takes source. When the response comes back from the UMass web server, which it will, with a source IP address now of 128.119.480 from the web server, it'll come back to the public-facing IP address with a destination port of 5001, right? Just source and destination IP ports will be flipped in the response. At this point, the router is going to say, aha, this port 5001 coming to my public-facing IP address, I know how to redirect it because I have to map it to 10.0.0.12345. Notice that this is always going to be the address in every packet that comes in, so this doesn't help you in demarcation. In fact, the router will store this address and just stored 5001 maps to this, same thing. Every single packet coming in will have the public IPs. The public IP doesn't help in this instance. It's going to remap that to the correct host from which that packet originated. So NACs allow you to send back responses to machines that originated the communication. Right? So now, let's go back to the question of, well, two people doing a Zoom call or a Skype call or any kind of a voice over IP or teleconference style communication from inside your respective homes, everything seems to work smoothly. If NACs can only respond to communication, not initiate communication from outside to inside, how are you able to communicate from inside to inside? Yeah?
I guess like Zoom has their own servers and maybe a server and that's recording.
Yeah, so this is a good time to segue to project 2 as well. How many people, I haven't seen as much chatter. Project 2 makes you do something very similar. So first let me explain what Tom's answer is, right? All of these services, voice over IP or teleconferencing services that seemingly work seamlessly from inside NAT to inside NAT, from residential networks, they all go through a server in the cloud. So your machine, if you want to initiate a Zoom call with somebody, it's going to first establish a connection to a Zoom application connection to a Zoom server in the cloud. That server that other site has already established a persistent connection. It's always there. So the Zoom server can respond back to the other guy saying, hey, you're getting a call from this entity. It can respond back because that connection always exists. And the whole call, the whole time, has to go through the server. It cannot move out of the server at any time. So all of your Zoom style calls, or really any voice over IP teleconferencing, or any application where the two endpoints are inside residential networks, they're all going through the cloud, through a cloud server. They cannot penetrate. Well, they can penetrate NAT if you set up holes. There's ways of penetrating NATs, but you have to do some setup to make that happen. Most of us haven't done any setup like that, but everything works seamlessly because we go through an intermediate cloud server. Okay, that's what helps all messaging. The Project 2 server is a similar messaging server.
Yeah, I was wondering, is that whole thing what port forwarding is?
Port forwarding is something that you can set up, yeah, for. So if any one of you others have done port forwarding, you want to have a web server at home. You don't want to keep it in the cloud. You're fine. You know what you're doing. You can administer it. You have confidence that your ISP won't go down. You can set up a web server at home, but if a web server is waiting for other people to contact it, in order to let outside communication come in, you of course will create DNS entries, but you can only create DNS entries with your public facing IP address. So when packets coming from outside, they need to know which is the web server inside the port 80 to which they should be directed. You can set up these things to allow NAT penetration. There's other protocols protocols or techniques of punching holes through NAT, but you have to do something to make that happen. Joe, right?
Yeah, how does BitTorrent work then? Because of peer-to-peer download.
Yeah. How's BitTorrent working?
I guess after like two peers connect to the server organizes like
The server is just a torrent or tracking server. It's just telling you which other peers exist. Data is not going. If data were going through the server, what's the point of it? What's the point of peer-to-peer?
yeah, the server will, after the peer connects to the server will know the public address that was up that here and the server really has 300 here.
If the server, like I said, if it's relaying all the chunks, the bytes,
Only the public address of the not the chunks of it.
that's not going to be enough. There's no way for a BitTorrent peer inside your house to establish any connection, any communication with a BitTorrent peer in somebody else's house. There is just no way. That is what I'm telling you. I saw a hand somewhere there, yeah.
So the server sends an address which is the WAN side address, and I essentially try to connect to the WAN side address, and it will forward it to the LAN side address, and that is how I establish a connection to another peer in the same NAT.
Okay, we need to be careful. We're on the route, right?
Oh yes.
There isn't a way, let's say this is peer A, this is peer B, okay? They're both inside a residential network, and this is the internet cloud, alright? Your Zoom calls are going through a Zoom server. So this is a persistent connection you have, this is a persistent connection you have. Just like in Project 2, everything is going through a messaging server. this is fine, right? Whenever the client starts up, it establishes a connection with the server. So when you want to make a call, it goes like this, it goes like this. B knows that A is going to call it, so they can all communication is going through this. There is no way after initiation of this communication for the server to move itself out. The whole call has to go through the server. In the case of Zoom or really anything happening like that. There is just no way at some point to say, okay, now that this hole or tunnel has been established, now we can just directly communicate. That's not happening. Max won't allow you to allow for that to happen. Unless people have done something like what Tom said, pull forwarding said. Okay, most people haven't done that, right? But everything seems to work just fine. So Joe's question, what happens in BitTorrent? How can these guys exchange blocks? It's not, so in BitTorrent you have a BitTorrent server tracker, right? What's the whole point of P2P? That you don't need to maintain a server. But if every piece of data needs to go through this server, it's not P2P anymore. You're not getting any benefit over client server. No.
I know there's something I think it's called like PNP.
Yeah, I'll come to that in 1 second. It's like, so it's along the port forwarding set. You have to do something to make that happen. So the answer is data is not going through the tracker. It's not the point of the tracker. Otherwise, then it just becomes a client server server. There's no point if you have to relay all of the data, right? Not just which peers IDs are part of this connection. So that's not happening. It's not going, data is not going through the tracker. If you do nothing special, peers behind NATs in BitTorrent will not exchange blocks. Neither can initiate a TCP connection to the other. Okay? There's many peers in a typical swarm with public IP addresses, so they can exchange blocks with this peer C, this peer B, and so on, but not A and B directly. Unless there's some port forwarding like setup that's being done in this router, or as Tom mentioned, another protocol called universal plug and play that many routers support that allows BitTorrent to punch a hole from outside to the inside. You have to also enable support here for UPnP. So this makes these applications a little more plug and play. But again, unless you do something explicitly, there's no way for NAT, behind NAT to behind NAT communication to happen. The direct communication has to go through an intermediary because first contact cannot be established from outside a NAT to inside a NAT unless you do something to make that happen administratively. Yeah?
Are NATs only for homes? Like what other examples?
No, they use it in enterprise networks. So this could be a small business. It's not just, so Amazon, for example, again, uses, sometimes it could be just for ease of maintenance, not necessarily for shortage of addresses. Sometimes it's easy to maintain an internal IP addressing that you don't have to change, that doesn't break LAN applications, to give the look and feel of all machines as if they're on the same LAN. That has its own benefits, but then keep the publicly visible IP addresses. Like how do people reach you, that part, separate from the internal management? So they just flip around from IP addresses. So public IP addresses in for EC2, for example, would be a different pool of addresses that can change over time compared to their internal IP addresses, which might be a separate pool and could change over different timescales entirely.
So like if you went to Amazon.com, that's like a publication IP, but internally there might be a ton of other like hosting teams communicating with each other.
Yeah. Yeah. So on that note, let me also get a quick, I'm a little concerned that there's not as much Piazza chatter about Project 2. So Project 2 is going through a messaging server. It's asking you to implement a reliable transport over UDP. Okay, it's due the 21st. I haven't seen as much chatter. I don't know if people are making steady progress or not. 2A, unlike 1A, 1A, the survey, I found that most people spend a total of, they said, around close to 15 hours median, not most people median, on combining Project 1A and 1B, which I think most of you spent more on 1B than 1A, so maybe 5 hours and 10 hours, something like that. But 2A is not like 1A. Like in 1A, if you just went back and actually did the socket programming hello world examples, 1A would have, you know, like, the solution I gave you was literally 7 lines of code, right? But 2A is not like that, or Project 2's split is not like that. The correctness part is, I'd say, easier than correctness and speed, but it's not like a few lines of code. Okay, correctness, you probably spend more time in part A and less time in part B, making it fast. So you gotta really get started with it at the earliest. Okay, we're here to help you, but start early. Okay? There's nothing that can help more.